All right, so hopefully you had enough time to think about it. Let's do it together. By the way, before we do this, the other problem that we had earlier was bugging me, so I thought about it. Remember the question with tangent inverse of x? Why do we include the -1? Of course, now in hindsight, it seems obvious because we had something like this. When we simplified it, we had like -1 to the n, like -1 to the 2n plus 1 over 2n plus 1, correct? I multiplied the tops by adding the exponents. I had 3n plus 1, and that wasn't obvious because 2n plus 1 is obvious. It's always odd, etc. 3n plus 1, to me, it wasn't obvious if it was going to be alternating, but it's easier if you look at it this way. What is -1 to the 2n plus 1 always? 2n plus 1 is always odd, but what is -1 to the 2n plus 1? -1 to an odd power is always going to be what? Think about -1 to the third. That's going to be -1, right? So -1 to an odd number is always -1. So what you have really is -1 to the n times -1. And what is that? -1 to the n plus 1, correct? Now, is this alternating? Yeah. Yes, this is definitely alternating. Does it pass the alternating series test? Yes, because 1 over 2n plus 1 goes to 0. Therefore, done deal, we can include x equals -1. So please go back to your notes and make that minor change. The interval should be inclusive, -1 to 1. Okay. All right, so back to this question. Okay, so we begin with the series for cosine x. Let me answer that question right after class because I already erased it and I don't remember what it was that you're asking about. So I'll get back to you on that one, okay? Okay, so we're going to start with cosine x. And first of all, we need a series for cosine of root x. Let's begin with that. So we want a series for cosine of the square root of x. So every x will be replaced by root x, right? So we'll have something that looks like this. 1 minus root x to the second power over 2 factorial plus root x to the fourth power over 4 factorial, etc. You know, these questions, in my opinion, are very elementary, but there are so many steps. If you try to do like 3 steps at once, it's also easy to make a mistake. So let's just make sure we show every step one at a time. Like we have a series for cosine x, but let's cosine root x, let's simplify it. This is the same as 1 minus what? X over 2 factorial plus x squared over 4 factorial minus x cubed over 6 factorial, right? Okay, now what we want is x times cosine x, right? So let's do that one. So what is now x times cosine root x? Everything on the top will be multiplied by x. Would you agree? Okay, so the x minus x squared over 2 factorial. We're multiplying everything by x. Okay, what should I be doing now? Integrate. The integral of x times cosine root x dx equals, integrate term by term, right? Which will have x squared over 2 minus x cubed over 3 times 2 factorial plus x to the 4 over 4 times 4 factorial, etc. X to the 5 over 5 times 6 factorial. Okay, are we in agreement so far? Any questions about what we have so far? Okay, okay, what we're going to do with this is think about the limits that were given to us. From 0 to pi over 3 were the original limits. So we need to decide, you know, where do you draw the line? Would you draw the line maybe over here or over here? We just don't know. It could be, maybe we need a few more terms, right? Since we're going from 0 to pi over 3, find the first term that is less than 0.001. That will be your error term, and you add up everything up to that point. Why can I do that? Because this is an alternating series. For an alternating series, we can do that. So let's do some trial and error here. I think that'll be the easiest way to solve the dilemma. So go ahead and plug in pi over 3. I'm going to plug it into this term to begin with. So I'm going to put in parentheses pi over 3 to the power of 5 divided by, in parentheses, 5 times 6 factorial. I think 6 factorial is 720, right? Yeah. Okay, what did you all get for that? I got 3.498, and e to the minus 4. Okay. So that's really 0.3 zeros and 3.498. Now let me make a note of it, because I don't know if this is how far I want, 0.0003498. Okay. Now let me also check the previous one, because if this one is less than 0.001, then I can even do away with less terms. So let me also check that one. So plug in pi over 3 into the previous one. I'm going to do second enter on my calculator. Instead of power 5, I make it power 4. And on the bottom, I change everything to 4 times 4 factorial. And 4 factorial, I believe, is 24. Okay, that one is not less than 0.001. So this is exactly the place we want to be. You find the first point where it's not less than, but the next term is less than the given error percentage. So this is where we want to draw the line then. Right here, the previous one, right there. Okay, so that means this will be our error term over here. This will be our error. And the correct answer from 0 to pi over 3 with an error less than 0.001 will be plug in the limits of integration only into the first 3 terms. Okay, and let's see what we're getting there. By the way, if you plug in the lower limit of 0, that doesn't give us anything to subtract, so we don't have to worry about it. We just have to worry about the series that has a pi over 3 in there for x. You could also convert pi over 3 to a decimal, but use plenty of decimals there, like 1.0472, maybe even a few more, because you don't want to do the rounding in the intermediate steps. You want to do the rounding in the last step. Anybody who added those 3 terms? 0.36944? And we're saying that this answer approximates the actual answer for the integral with an error less than 0.00035 roughly. So it's a pretty good approximation for the actual answer. But keep in mind, the further away you go from 0, the worse off the approximation, the more terms you're going to need to add. Pi over 3 was a pretty small number. It was close to 0, so we didn't need that many terms. Could you check this answer on the calculator? There's an integration key, right? FNINT under the math menu. Make sure you're in radian mode, because you're integrating something with a trigonometric function in it. Then you would just integrate x times cosine of root x. Let's do that one together on the calculator, because for these questions you have a way to check your answer, so why not? We should go ahead and do that. Where is my calculator? There it is. So integrate. Oh, somebody changed the color here. It seems not me. Okay. Let's see. So we want function integration. Go under the math menu. Option number 9, I believe, is the integration option. But I need to get rid of that a there. Okay. Then we want to integrate x times cosine of the square root of x. Cosine of the square root of x. Make sure you close all of those parentheses. 1 for the square root, 1 for cosine, comma, what do I usually put? X for the variable, and then the limits 0, comma, pi over 3. Okay, we close it and press enter. Hopefully it works. There you go. 0.369 to the nearest 3 thousandths. What do we get over there? Something really close, right? 0.369 to the thousandths accuracy. You know, our answer is definitely matching the calculator's answer there. And if you take the difference between that calculator's answer and our answer, we should be able to see that the error is less than 0.00349. Okay. Well, maybe somebody could do that checking for us, just out of curiosity. Can you take the calculator answer, which is this one, and minus from that our answer, which was 0.36944, and what do you get as the error there? The actual size of the error. Assuming, of course, that the calculator is doing a good job there. Okay, so verify that the error will be very, very small, basically. Okay, now let's. Okay, so I'm going to give you a homework question. It's going to be this one, and we'll talk about the answer next class. Actually, I'll give you two questions. Integrate sine of x squared from 0 to 1. And I made it a little bit easier for you this time. I said use the first 3 terms. So it's given ahead of time how many terms you need to use, but then estimate the error. Then I'm going to give you one more integral question. Did you guys get this one? So integrate sine of x squared from 0 to 1. That's one of your questions. Okay? And it says use the first 3 terms. Okay? And then there's going to be one more. And that will be this one. Excuse me. Integrate this quantity, e to the negative x minus 1 on the top, divided by x on the bottom. We want to integrate with an error less than 0.001. From 0 to 0.7, those are the limits of integration. From 0 to 0.7. And you can assume that the expansion for e to the x is given to you. Like on the last question, you can assume the expansion for sine of x is given to you. Okay, so these are 2 questions I'd like for you to think about, and we'll go over them on our next class. 0.7, yes. Yes. Right, you don't have to write it in so many words. You really need to just make sure what you wrote the integral correctly, and that's really all there is to it. With an error less than 0.001, that's all we need there. The other one said integral of sine of x squared from 0 to 1, and use the first 3 terms, and estimate the error after that. E to the negative x, right. This problem has e to the negative x minus 1.
No, the thing in red.
The thing in red is giving you the expansion for e to the x, basically, which is something you already know. Okay. Okay, we're going to take a little bit of time to get an introduction on this, and we're going to finish this next time because it's going to take more time than we have left in today's class meeting. This is a really, really neat series. It's called the Binomial Series, and we've already done some work about this. You know, anytime you have like 1 plus x to the 1/3 power, or 1 plus x to the square root of 1 plus x, or basically we've been using about this. And what you see on the first slide here, which is also on your handout, is a review of what you already know from Precalculus. If you don't remember it, I'll go ahead and review it with you. From Precalculus, right, Pascal's triangle, if you said that, you're remembering things in the right direction from your Precalculus days, okay? Basically, in Precalculus, you learned how to expand a plus b to the kth power. Think about a plus b to the 2nd power, just for the ease of argument. So it would be like a to the second power, you would have a middle term, and then you would have b to the second power, right? But if k is like 4 or 5, then there are more terms in the middle, right? And the way it works is you decrease the powers of a and increase the powers of b each time. And there is a different coefficient which comes from Pascal's triangle, also represented by NCK, or in this case, combinations of k choose n. So this was a theorem you saw in precalculus. So why are we revisiting it then? Aren't we done already with this already, right? Well, you were done with it, but that only works for whole number exponents, like k being second power or the third power. What do you do if your power is to the power of negative 1/2 or to the power of 1/3, or you name it? Then you need something else. Then you need Newton's, Sir Isaac Newton's, genius skills, and he was the one who expanded this formula to when you don't even have a whole number. What happens then when you have, when k is not a whole number? It's still possible to do it, and there are so many physics applications. And the back of your sheet has one application, which we will do next time. There are so many places in physics. They have exponents, and they're trying to evaluate them. Like here, it would be power of -2 in the example you have on the second page. How do you simplify to the power of -2? So the way to do that would be by using a Taylor or Maclaurin series expansion. So if you're trying to get a Maclaurin series for 1 plus x to the k, what would you do first? You need to get all the successive derivatives, right? And derivatives are very easy in this case. The derivative of 1 plus x is 1 plus x to the k. What is the derivative of that? K times 1 plus x to the k minus 1, correct? Differentiate it again. That brings the k minus 1 down. Then you have k minus 2 power. So keep differentiating it. At the same time, plug in the values 0 for x because it's a Maclaurin series. If you plug in a 0 for x here, what do you get? If you plug in 0 for x, you get k, which is this, right? If you plug in 0 for x here, what do you get? K times k minus 1, right? Plug in 0 for x here, what do you get? K times k minus 1 times k minus 2. So you do this all along, and you end up with a power series that works even for when k is not a whole number. And the series is over here. And it converges for values of x less than 1. And they say that you should check the endpoints for different values of k changes. Sometimes the endpoints converge, sometimes not. It depends on the value of k. So if you look at the example you have on the back of your sheet, find a power series for example, let's do the second one. 1 over 1 plus x squared. 1 over 1 plus x squared. Exactly. You would put it like this. 1 plus x to the power of -2. And I'm going to copy that information from the previous page. I'm going to copy the binomial series. You have it on your handout. You don't have to copy it, obviously. But I'm going to copy that boxed information. So we can just plug everything in there. So this was the binomial series. It works for any k as long as x is between -1 and 1. It doesn't have to be whole number. It can be negative. It can be fractional number. That's the beauty of this expansion. So in this case, k is -2. So can you write the first few terms, assuming that k is equal to -2? So it says the first term should be a 1. No problems there. What will the next term be? We're going to follow directly from here. What is k here? Exactly. So it's going to be -2 times x. Okay, what would the next term be? -2 times, what is k minus 1? -3. divided by 2 factorial times x squared. Okay, what would the next term be? Remember, k is negative 2. Negative 2 times, negative 3 times, negative 4 times, x to the third over 3 factorial. There's an easy way to remember this. If you're writing the term for x cubed, you need to multiply 3 numbers on the top. Starting with the power, you keep subtracting 1 at a time. You need 3 numbers being multiplied. If you have the power of x squared, the coefficient of x squared, you need to multiply 2 terms on the top. And if you simplify this, what do we get? One minus 2x. What's the next term going to be? Plus 6 over 2, which is plus 3x squared. Can you guess the next term? Or just obtain it? 3 factorial is 3 times 2, right? So those are going to cancel with the 3 times 2 on the top. What are we going to be left with? Negative 4. What am I missing? Cubed. Okay, I did this example because the application problem you have on your handout is going to require this example. It's a really interesting application problem. I want to talk about it because I want you to look at it before you come back next time. It's the question about, usually how many of you have heard force equals mass times gravity, mg, F equals mg? Oh, yeah. Unfortunately, everybody thinks that's the correct formula, right? But that's only true if you are close to the surface of the Earth. There's a more general formula which you have on the bottom of your slide here. So what you're going to be doing on that example is you're going to be using a Taylor series expansion or a Maclaurin series expansion. You're going to write this expression as a Maclaurin series, and you're going to see that for values that are close to Earth, or if you just take the first term of the Taylor series expansion, you end up with force equals mg. So think about that question. I would like for you to also finish the other problem up there in your handout. This one. So you have your group activity to complete, and you have several homework questions from this lesson. Also, please remember to print out the worksheet, the review sheet for the test, because we're going to try to finish up all the little leftovers, hopefully in the first half an hour, and the rest I'm going to give you guys for reviewing for the test. Okay.
So what we did there.
Okay, I think I'm going to continue the recording for our online students. And first of all, to finish off what we were just doing a moment ago, to get the series for 1 over 1 plus x squared, a student asked, can we write this as an infinite summation notation with a compact sigma notation? There definitely seems to be a clear pattern here, so we should be able to do that. So let's give it a try. Let's see. So we want a summation of, first of all, this is alternating, so we're going to need something like negative 1 to the n or n plus 1, which we can adjust in just a little bit. Then we have x to the power. Let's say that x to the n. But then there are also coefficients in front of n, and the coefficients seem to be 1 larger than the power n itself. Like x cubed had a coefficient of 4. So I'm going to put an n plus 1 in there. And where to begin? If we begin at n equals 0, that will give us a positive first term. The coefficient will be 1, and x to the 0 is 1, so we get 1. If n is 1, we get a negative. The coefficient will be 2, and x to the first power, so it looks like this is going to work. So this would be the power series for 1 over 1 plus x squared in compact sigma notation, and this is the one in the long written out format. We're going to be doing an example in just a little bit. Actually, let me see if I can find it. But before we go to the example that makes use of the series, it's a nice application problem. I just want to give you a little bit of time to get some more practice with the binomial series. So please take a moment to think about how you would expand the cube root of 1 plus x. Again, remember the binomial series, the beauty of it is that it doesn't require whole number integer values for the powers. It doesn't require negative or rather positive values. It works with any power, basically, any real number power, whether it's a fraction or negative number or positive. Like in this case, you have 1 plus x to the 1/3 power. Still, that formula will still work. So think about this one. And if you like a challenge, I will also show you another one to think about. A power series for 1 over the square root of 4 minus x. And the idea there would be try to write it as 1 plus x or 1 plus or minus x under the square root, because the rule only works under those situations. So think about what you would need to factor out, how you could rewrite this. Now, since the exam is coming up real soon, I'm going to go ahead and show you the solutions to these. However, if you could pause the video here, try it, or maybe fast forward the solutions at the moment and come back to them, because I really want you to think about those answers. But at the moment, I will show you the solutions. Okay, so I'm going to keep these up for just a little moment. Again, if you have already thought about the problem, then you can just check your answer. And again, if not, please pause the video, do the work, and then come back to this page. So for this one, we just wrote the first few terms of the cube root of 1 plus x using the binomial series. We've already done the other one earlier, 1 over 1 plus x squared. And I'm also going to put the solution up for this one in case you are interested. Again, I hope that before you look at the solution, you would have tried the problem, or else fast forward this, like I said, come back to it after you've had the time to think about it. Okay. Now I'm going to go to an application problem using a binomial series, and I think these applications are really neat, especially if you've taken some physics or if you enjoy physics classes. And even if not, hopefully you'll get something out of it. Okay, here's our first application problem. So we're given an equality here. This force equals mg times big R squared divided by big R plus h quantity squared. And here big R represents the radius of the Earth. M is the mass of an object on the surface of the Earth, or a little bit h units, h kilometers away from the Earth. And g is the gravitational constant. And what we're given is, let's read it together. It says the force due to gravity of an object with mass m at a height h above the surface of the Earth is given by this equation. First of all, they want us to express this in terms of a power series. And instead of using x as our major variable of the power series, they want us to use h over r. And if you think about it, h over r is going to be a very small number, because r is the radius of the Earth, h is the distance from the surface of the Earth for the object, and h is usually going to be a small value, r is a very large value, and the ratio is very small. So when we expand the series in terms of h over r, remember the binomial series, you want x to be less than 1, and the closer you are to 0, the better the approximation is. And h over r, chosen for x, again, that will be a value very close to 0. That means that we can use just the first term or just the first few terms of the power series expansion to get a pretty good approximation, because we are going to be very close to 0 in terms of our choice of x. And the nice thing about this problem is they want us to show that for values of h, first of all, they want to show that if we first use the first term of the series, only the first term, we will get force equals mass times gravitational constant, F equals mg, which is a formula most people would be familiar with. So in a sense, what we have here is the more general version that applies to objects that are much farther away from the Earth. So first we're going to show that in the local or closer distances that force would really be equal to mg, the formula that we're so used to seeing in physics classes. And then we're going to find out, we're asked to estimate the range of values h for which the approximation is accurate to within 1%. So we want an error of less than or equal to 0.01. Okay, let's start writing a power series for this function f. And we want to do it in terms of x equals h over r. We want to expand it around h over r. Now, to get an h over r in this expression, in the denominator, I'm going to divide everything by r. But that will have to be done inside the square. Let's see what I did here. Okay, first of all, I have divided everything in the denominator by r because I want to get that h over r right there. But by doing so, because it was under a square, in a sense, basically the net effect of doing that is multiplying everything by 1 over r squared. So to undo the effects of that, I put a times r squared on the outside. Now this r squared on the bottom and the r squared on the top, they cancel. This one cancels that one. So we're left with the following: mg on the top, and r over r, of course, is 1 plus h over r squared. So again, in this first step, I was trying to get an h over r in the denominator. So I started by dividing everything inside that parentheses by r, and I had to consider what the net effect was so that I had to undo the effects to keep everything the same. Okay, now, we're trying to write a Maclaurin series expansion. Rewritten, the above expression gives me mg times 1 plus h over r to the negative second power. We're supposed to use x equals h over r, and k is negative 2, that's our power, and we're going to use this in the binomial series expansion. Now let's remember what that series expansion was. We've just seen that earlier in this lesson. This is 1 plus x to the k. We're going to use k equals to negative 2, and we're going to use x is equal to h over r. So let's plug in that expression, continuing from this line basically. Continue right there. mg is still in there. So where I see 1 plus h over r to the minus 2, that's where I'm starting to write the terms of the binomial series. So I have the 1, k is negative 2, x is h over r. Then this represents the second term because k minus 1 is negative 3, and h over r has been now squared because x has to be squared. So as you can see, I can write the terms like that. Now it's a little bit cleaning up. I cleaned up the constants a little bit. And take a look at what happens if we only use the first term of the series expansion. So what happens is the first term is 1. So what you end up getting force equals m times g. That's the very familiar formula that we have seen in a typical physics class for force. By the way, instead of recreating the binomial series like I did here, you could have also done this. Just moments ago, we did the binomial series expansion for 1 over 1 plus x quantity squared. And for that expansion, we had gotten this quantity, if you recall. So basically, that's exactly what happened here. 1 minus 2 times x plus 3 times x squared. But our x was h over r, you see? So that's the only difference there. Okay, so as we can see, if we use just the first term, we're going to get force equals mg. And this is an alternating series, so the error will be less than the absolute value of the next unused term, which is 2h over r. And we're given that r is equal to the radius of the Earth is 6,400 kilometers. And we're trying to make sure that the error is less than 0.01. So if we solve that inequality, multiply both sides by 6400 and then divide by 2, you will get the requirement that h be less than 32 kilometers. So as long as the object is less than 32 kilometers from the surface of the Earth, then using F equals mg will be a relatively good estimation. It will be a good estimation for the force exerted upon that object. And for distances beyond that, that means physicists need to go back to that longer version of the formula that we saw earlier, and they need to be using that one. So I thought this example was really cool because the higher levels you go, the more you refine things you've seen in the past. And I think that's what's happened in a lot of the areas of physics. Excuse me. Like this next example is going to show us as well. Okay, let me give you a moment to read the question first. Again, those of you who've taken physics classes would be very familiar with this formula, that kinetic energy is one half mv squared, and m sub 0 here represents the mass of the object at rest. Now, Einstein's theory, and I'm no expert in it, but this is a very famous formula. Basically, he claims that the mass is actually changing as the object is moving at very, very fast speeds. But if you think about it, for objects that are moving very slowly, slowly in comparison to the speed of light, c represents the speed of light. So if v is relatively small in comparison to the speed of light, v squared over c squared will be a very small number. And 1 minus that will be almost the same as 1. So for us earthlings, people who move at, 100 miles per hour or even a few hundred miles per hour, let's say on an airplane, that's as high as you might get. As you can see, even for that, the denominator will be almost 1, and the mass as the object is moving will be the same as the mass at rest, which is this one. So there isn't a lot of changes happening. But Einstein he refined this for objects that are moving very, very fast, and then he said that the mass of an object will be given by this equation. Also, there's a definition here. Definition of kinetic energy is, it's defined as mc squared minus m sub 0 c squared, where m sub 0 is the mass at rest, and m will be the mass as it's moving, because again, it's supposed to be getting heavier as it moves at very fast speeds. So our job is to show that this complicated looking kinetic energy formula actually boils down to what we've seen, hopefully, if you've ever taken a physics class, that it will boil down to this 1/2 mv squared. And even if you have not taken a physics class, we're going to try to show this equality, that this more complicated formula boils down to 1/2 mv squared when v is much smaller than c. And to do this, we're going to expand it in terms of v over c. So first we start by writing the kinetic energy formula, which is mc squared minus m sub 0 c squared. Again, it's the difference between its total energy and energy at rest. That's the definition of kinetic energy. So I factored out the c squared in the next step. And then here I'm plugging in what m was in terms of what it was given to me earlier up there. So m has been plugged in this equation. I will also factor out m sub 0 in the next step, as you can see, which I have done here. And then I'm going to rewrite everything as a power, because I want to use the binomial series. So the 1 over square root of that quantity can be written as that quantity to the negative 1/2 power. Okay, that is the part where we're going to use the binomial series, because that can be resembled to 1 plus x to the k. Think about, what is our k? the power, which is negative a half. Think about what is our x here, because the typical format is 1 plus x. So over here, our x will be negative v squared over c squared. So we're going to expand this using the binomial series. I will leave c squared times m sub 0 right where it is. That was already there. For this quantity here, we're going to go ahead and plug in the binomial series. Remember, k is negative a half, and instead of x, I'm writing negative v squared over c squared. So you have k times x. Then you have k minus 1. Then you have x squared divided by 2 factorial. And you could go on like this, but we were only going to need a few terms. And don't forget, there was a minus 1 there and a minus 1 here. So now the plus 1, minus 1, they cancel. This one will cancel with this one. So let's see what we have left. And I can clean up the constants a little bit. Like over here, it's really positive a half. Over here, multiply them. And once you clean up the constants, you come up with this equation. So for values, when v is much less than c, this ratio is very small. Remember, c is the speed of light. So in most circumstances, v would be much less than c. So v over c would be a quantity very close to 0. And therefore, all these higher powers of v over c are going to be negligibly small. The only one really that's going to be dominant is the first one, at least as far as approximations are concerned. So if we just take that first one, we would be left with c squared times m sub 0 times v squared over 2c squared, and now cancel the c squares, and voila, that was the formula that we're trying to show. Again, under certain cases, in the case of velocity much less than speed of light, then we can abbreviate kinetic energy as just simply 1/2 m sub 0 times v squared. So there you have it. You never thought you would be studying some math behind relativity physics, but I just thought this example was really cool, so I wanted to share it with you. And finally, I want to leave you with an example to think about in the same lines that we've been discussing so far. I'm going to leave it on the screen. Please read it, copy it down, and if you get a chance, think about it. Okay, I'm going to stop the recording, but again, you can certainly pause it at that moment and be able to copy the problem completely. And then if you have any questions, please post it on our bulletin board.